Good morning. Welcome to Krishna's classroom. In the last lecture, we gave some preliminaries on the implicit function theorem. In fact, we motivated it from examples and gave an idea what it means in geometrically. Now we are in a position to give the formal statement of the theorem and then the proof of it. As I told you earlier, that this theorem has been proved using the fixed point theorem, and that's a part I want to emphasize here. It's fascinating to see how this has been formulated as a problem in the fixed point scenario, and how the conclusions have been arrived at. This is, of course, the two-dimensional version. It's working in R2, but of course it can be generalized. In fact, I have done a very elaborate discussion on this theorem, as I mentioned last time in my lectures on analysis on Rm. Please refer to it. It takes 3-4 lectures or at least 3 lectures to cover the whole idea in a more general setting. But we will revisit this again in the context of the metric spaces discussions that are going on. So it's almost a repetition of what has been done. But nevertheless, let us do it. Well, before I go to the statement of the theorem, which is already there on the board, I wish to return to the examples and probably give one more example. The first one of the examples that we considered was this. In R2, we have taken the unit, or say not necessarily unit circle. We have taken the fxy to be equal to x square plus y square, and then of course this is of course the set x square plus y square equal to a square, with a as the radius. Now what we have observed is the following. The theorem says the following. Suppose you take a point on the surface x square plus y square equal to a square. Okay, say x naught y. Then you have x naught square plus y naught square equal to a square. Except for 2 points on this circle, everywhere else can find a neighborhood of this point in R2, and the intersection of the curve that is determined by the x square plus y square equal to a square with this neighborhood given by this portion of the arc or the arc of the circle that I have marked can be written as a function of y as a function of x. That means you can solve this equation x square plus y square equal to a square in the form y as a function of x in the neighborhood of a point x naught y naught, in some neighborhood of x naught y naught lying on this, except possibly at 2 points. The 2 points where it fails is 0, 1, 0 and minus 1, 0. There you see that the Fy at 1, 0 equal to 0, Fy at, and what it says is this: if Fy at xy at x naught y naught is not equal to 0, then there is some neighborhood of the point x naught in which the equation x square plus y square equal to a square can be solved in the form y equal to y as a function of x. Okay, that means there exists g defined in for some epsilon positive such that f of x gx equal to a square. Now this is the form of the theorem that we have, and slightly differently formulated. We take the function to be x square plus y square minus a square, and if you take that form, then it is going to be okay. So if we take the expression f of xy to be x square plus y square minus a square, then you see that this g will be for every x and y in x naught y. X naught minus epsilon to x naught plus epsilon. Now there the crucial condition is this, and what happens when f at the point 1, 0 and 0, 1, minus 1, 0. No matter how small a neighborhood you take, you will see that this arc, that is relevant to be written as a g as a function of y as a function of x, fails to be a function, because you see that, this is the sort of arc, this is the sort of situation that you have. Suppose this is 1, 0, then see that take any neighborhood of this, no matter how small epsilon is. You take an x here, corresponding to any x here, there are no values here, but that doesn't matter. But suppose you take x here, then gx takes 2 values, so no function is defined, no function g is defined on this interval, so that the stipulated condition is valid. Yet another example which we have not looked at is this. To take f of xy equal to x square minus a square. Then we are, this is the first example. The second example is f of xy equal to x square minus a square. Now you can see that f of xy equal to 0 is a pair of straight lines. This is y equal to x, y equal to minus x. Or this is y equal to x, this is y equal to minus x. So this pair of straight lines that you see here is the 11th curve. Now what we are asking is it possible that at every point you can express this in some neighborhood of that point? You can express the portion of the intersection of this curve with that neighborhood as in the form y as a function of x. See, as you can see, the only point where you are going to have trouble is at 0, 0. Where you see that if y is not different. If y at 0, 0 is not different. That's the problem. Okay. So there are two things. Fy equal to 0 and Fy not defined, this kind of points may give a trouble, because you see that if you take any point, this point, and take a neighborhood of that would be something like this. And you see that in this neighborhood, the section of the curve intersected are these two line segments. And any neighborhood of 0 you take here, then you cannot express this as a function of y as a function of x, because corresponding to x, there are two values of y determined except at this point. Everywhere else it is two values are determined. And there the difficulty is that Fy is not defined. So if Fy is not defined or Fy is 0, such points do create problems. Everywhere else, anywhere else, you see that you can find a neighborhood in which a portion of the curve intersected in this neighborhood can be expressed as in the form y is equal to a function of x. Everywhere else it is possible. Okay, that is one remark. The second remark is this. Suppose, so here you have tried to look at x as the independent variable and y as the dependent variable. If that is the case, then the condition that emerges is that Fy at the point x0, y0 is not equal to is not equal to 0, then only you have g defined. Suppose I wanted to say something. Suppose you want to consider y as the independent variable and x as the dependent variable. That means in that case you will be trying to solve this equation f of xy equal to 0 in the form x as a function of hy on some interval. Okay, that's the meaning. In that case, the corresponding condition is going to be that fx is not equal to 0. So this is the other way in which you can make this up. And you see that 1 0 0 1 minus 1 0 is no difficult points as far as solving this in the form x is equal to a function of y. Whereas in that case, these 2 points 0, 1 and 0, minus 1, they become points where things do not work. In this case, this is the only place where neither Fy nor Fx is defined. What I want to say is both Fy and Fx are 0 at this point. That's the difficulty. Okay. So you won't get this in the neighborhood of this point, either in the x neighborhood of this point or in the y neighborhood of this point. This does not solve y as a function of x or x as a function of y. So that's the scenario that you. Now we are in a position to state the theorem and then work on it. So let me just come back to the statement here. Recall these examples. They would give you the right guidance, or this explains the geometry of the problem, but this would give you the geometry. This would give you the idea how things are posed. So, general situation is this: U is an open subset of R2. So, we are working in R2. U is an open subset of R2. And F, so it's something like this. So, you have the point x0, y0. Oh no, so see, you have this is the map that you have. And we assume that F has continuous partial derivatives Fx and Fy on everywhere on it. Assume at x0, y0 belonging to U, f of x0, y0 is equal to 0. So here f vanishes. And the partial derivative of f with respect to y is not equal to 0. If that is the case, then there exists, suppose this is the point x0, y0. Now this is the point x0, 0. It says that suppose that the curve is something like this, where at this point the Fy, that is the derivative, that is the curve does not take a vertical position. That's it. So it's not something like this. So that you have a problem here, like the case of the circle that we have encountered. And if so, what happens? It says there is some neighborhood x0 minus epsilon to x0 plus epsilon, in which the function, the intersection of the curve with the neighborhood we have chosen for x0, y0 is represented in the form y is equal to g of x. So that f of x gx equal to 0 for all x belonging to x0 minus epsilon to x0 plus epsilon, and G is a differentiable function on its domain. That means on the interval x0 minus epsilon to x0 plus epsilon, and G derivative at x is given by minus of fx divided by fy. And I have explained a lot of things to compare the whole problem with the tangent. Now you see that the problem, see the curve is solvable, or the equation is solvable in the form y is equal to function of x in some neighborhood, provided at that point x0 y0 the tangent to the curve is not along the y direction. Okay, so that's the point. Okay, the tangent to the curve is not along the y direction. This is the condition. So the tangent there is yet another condition which I will come to. Curve of intersection is not along the y direction. That's the meaning of saying that the partial derivative of f with respect to y is not equal to 0. The other scenario that we have looked at, where you have pair of straight lines and look at the intersection. At this intersection, you see that you are going to have trouble. So if this point is x0 y0 and your function f is f of xy equal to x minus x0 into y minus y, then you are trying to solve f of xy equal to 0 at here. You see that both fx and fy are 0 at x0 y0. Therefore, you see that there is no well-defined tangent to the curve at the point x0 y0. That's the problem. Okay, in either case, the tangent becomes vertical, or the tangent to the curve at the point is not defined at all. In either of these scenarios, you see that you cannot solve it y as a function of x in some neighborhood of x. This is the content of the theorem. Now we take up look at the solution of the proof of this theorem. So let me take out the statement of the theorem. Hope all of you have it printed in your mind at this time, or you can always go back to the lecture. Make note of it now, because of space constraint, I have to take it out. Okay. Now let us see how we formulate the proof of this theorem. So we have the following. F is from U to R, and at x0 y0 belonging to U, we have f of y not equal to 0. These are the assumptions that we are. Okay. Now in this scenario, we have seen two situations where either Fy x0 y0 at x0 y0 may not be 0, and the consequence is that the curve that you have determined by f of xy equal to 0 passing through the point x0 y0. It passes through the point x0 y0 because you have f of equal to 0. And what we have is that you take the portion of the curve at the point x0 y0. See, at the point x0 y0, suppose this is the point x0 y0, then the tangent to the curve is well defined and not vertical. That means not along the y-axis. Okay, so this is Fy. Okay, the slope of this would become what you have. It's minus fx by fy. So if fy is 0, then this is not well defined. The tangent to the curve is not well. That is the curve, the curve that solves the equation is not. That's the problem. Sometimes both fx and fy may be 0, as you have seen the case of pair of straight lines at the point of intersection. There you see that this is not the slope of the tangent to the curve is not defined. Okay. So these are the two conditions under which things go wrong. So in short, it's all both summed up by saying that Fy at x0 y0 is not equal to 0. Takes care of all these situations. So let us prove this theorem. What one does is, so this is what you have. You have U so this is the point x0 y0, and this is the portion of the curve equal to 0. Therefore, in particular, f of x0 y0 is equal to 0. So what we assert is this: take such a point, take an open neighborhood of that, and the portion of the curve that is intersected is given by this, and you see that there, what you say is that there exists, suppose x0 y0 is a point such that fy x0 y0 is not equal to 0, and of course f of x0 y0 is equal to 0, then well-defined tangent here, which is not in the vertical position. There's a well-defined tangent here for this curve, this portion of the curve, and this can be written as y as a function of gx, so that f of x naught gx naught is equal to 0. If x naught y naught is 0, and f of gx equal to 0 for this one. So you are talking about that, and there you see that what we assert is that there is a well-defined tangent. The slope of the tangent is given by minus fx by is the slope of the tangent, and this is well defined. Okay, so there is a well defined tangent at that point. Then it is, see, the point is this: suppose you consider the curve as this line, then what happens? Everywhere, in every neighborhood of x naught, it is solvable. It is defined on the whole of R2, or the line occupies, the line is something that stretches from one end of the space to the other, and you see that the line can be solved, rewritten as a y as a function of x. This is the idea. Suppose f of xy equal to ax plus by plus c, and we are taking a point x naught y naught such that this is equal to 0, then you see that the geometry is this, and what we have assumed is that fy is not equal to 0. This is equal to b, which is not equal to 0. So you are assuming b is not equal to 0. In that case, what it says is this: if you take the equation ax plus by plus c equal to 0, then you can write this as by equal to minus ax minus plus c, put in the bracket, and then since b is not equal to 0, you can write this as y as minus 1 by b, and this is defined for all x. Okay. And explicitly you see that a f of x y equal to, I'll write y as gx equal to ax plus by is b into minus x plus c, and this is equal to ax minus ax plus c minus c. So g has the property that f of x gx is equal to 0. Okay, and this is valid for every x. Listen. Now, when the function is a nonlinear function, when it's a linear function, this sort of thing happens. But when it is a nonlinear function, what happens is that this is ax plus by. When it's a nonlinear function, the same result can be asserted only in some neighborhood of x naught, y naught, provided it is a well-defined tangent at the point x naught, y naught. This is the This is what we state. So now let us see how we prove this theorem. Okay, so we go to the proof. Now those who want a very deeper analysis of this, you should go to my lectures in calculus on R. There, of course, a more general scenario is sorted out. And I think I make take up these kind of examples and then try to give you an idea of what the theorem is or how it's a question of formulating the proof. Okay. So as I said, our trump card is the fixed point theorem. So we have to rework the whole thing such that you can apply fixed point theorem. Okay. So what the art of doing this is, see, we are working with this one. F of xy equal to 0 and try to solve this. What we do is, generally the mode in which we try to rework the whole thing is, you add and subtract y to it. Write it in this way. And then write this as a new function. Therefore, now the problem is reworked formally to ask the following question. Now you see that the conditions of f will determine the conditions on h. Okay? In that case, what do you do? The problem is find y such that hxy equal to, or seeking a fixed point for this. Now we have to say where we are going to define what is this y. Y is going to be a function. So it's going to be a function of x eventually. So you are seeking y as a function of x. Okay. So what you are looking for is this. And this you can rewrite as t of ys. So this is what you have. You have the new equation ty defined as, what is it? F of xy plus y. Now you are looking for the situation. So t maps y to some function. For any y, there is a function. So you have a class of functions now. So you have a space consists of all these y's. On this space, t is defined. Now t is defined as a, or we formulate it in such a way that t is defined from x to x. Okay. And then we are asking the problem, does there exist a function y of x such that t of, what is this? This is equal to g of, or h of x yx equal to y of. So yx is a function. So y equal to y of x is a function of x which satisfies the given equation. Okay, and if you rewrite the whole thing, what does this mean? This means that f of xy plus y of x, which is, if I leave, zero. So that's how we reformulate the whole problem. Okay. Now a lesser scenario is the following. Suppose you want to find the zeros of a function. F defined from, say, some interval I to R. Say I you take as A. Then what you are looking for is this. Then you say x naught is the zero of this function. In that case, what you do? What you do normally is the following. Okay, you reformulate the problem. Reformulate the problem in this way. Then look at the problem gx equal to x. Okay. So what this problem is, now this problem is equivalent to this problem. So if x naught is such that f x naught equals 0, implies x naught equal to x naught. And this is, if fx naught equal to 0, then fx naught plus x naught equal to x naught, and then gx naught equal to x naught, or this is a solution of the equation gx equal to x. So it's a fixed point. So x naught is a fixed point of, that is another example in one dimension, which is more easily something that you can conceive. It's a similar problem. Okay. Therefore, we shall now try to formulate it. So a lot of thinking has to go behind this to properly understand the problem. Otherwise, it becomes quite complicated and messy. So the first job is to reformulate the problem into the language of to a situation where you can apply the fixed point theory. So we define the form. Inverse of that. And you know that this is fine because df by dy is not equal to 0. Now what we are looking for is a gx. Or some epsilon positive. And a function g from such that f of x gx equal to 0 for every x belonging to and this is equivalent to finding G having the property Gx minus 0. That means point for okay, let us rework the whole. Now it is possible. So let us, our job is now to rework it. So we have, this is just roughly the formulation that we have. Okay. Now we have f of xy in every neighborhood of where not equal to 0. And also have all sorts of smoothness. And we further have f of x naught y naught is equal to y. So also you take df by dy at x naught y naught. What is this would become? 1 minus ef by dy at x naught y naught, and this will be 1 minus 1. So this is equal to 1 minus 1, which is equal to. So these are the two things that you. Now we start making things rigorous. Since df by dy at x naught y naught is small, so this is equal to 0. Small for xy near x naught y naught, because it's a smooth function that you are having, and at x naught y naught it is equal to 0. This is the point. At x naught y naught this is equal to 0. Therefore you see that in some neighborhood of x naught y naught this is going to remain small, and therefore different from 0. So let us use that. Now there exists delta 1 positive and delta 2 positive such that mod x minus x naught less than delta 1 and mod y minus y naught less than delta 2 implies mod df by is less than or equal to half. Okay. Now df by dy is 0. Okay. Therefore, you see that you can find the point x naught y naught you take. You can work out a rectangle around the point x naught y naught, and this is delta 1, this is delta. So this is the rectangle I am talking about, where you see that df by dy is less than or equal to half. So the delta 1 and delta 2 has to be chosen in such a way, because the function df by dy is smooth and is equal to 0 at here. So you don't go too far so that df by dy is greater than half. That can be done. Now we may further assume by choosing delta 1 smaller if necessary, that f of x y naught minus y naught is less than or equal to delta 2 by such that mod x minus x naught so we have gravitated to this portion where you see that df by dy is less than or equal to half, and what more you have? See, you have a f of how do we defined f of xy to be, so recall that we defined f of xy to be, take out this, we have f of xy defined as inverse now we have this one, so f of xy minus y, this is another function of, this is equal to minus so you now work it out at the point y naught. Okay, so what f of xy at y naught minus y naught is estimated as this one, and this is of course as it is, it's not equal to 0. So you get f of x y naught. This is what you get. Okay, and then you see that this is not equal to 0, therefore 1 by this is well defined. Okay, and therefore you can choose your delta 1 if necessary such that this whole thing is less than delta 2 by 2 for mod x minus x naught less than 9. That is possible because of the continued smoothness, etc. Because you see that f of x naught y naught is equal to 0. Therefore, it is possible to do. So you can you can reduce the neighborhood of x naught in such a way that there this condition is satisfied. Okay. Right. So we have now arrived at, so we have the point x naught, y naught, and then you have a rectangle surrounding this, and this is essentially mod x minus x naught less than delta 1, mod x minus x y minus y naught less than delta. This after all this redefinition etc. is done, so we get a rectangle. And what do we have? We have capital small f at x naught y naught is equal to 0. Okay, right. Now we will define a space x to be defined as the set of all G which is continuous on the interval x0 minus delta 1, x0 plus delta 1. Continuous function is defined on this such that G at x0 equal to y0, gx minus y0 is less than or equal to delta 2 whenever mod x minus so this is the rectangle on which this particular property is satisfied. Okay. Now on this space, define the metric G1, G2 equal to supremum of Gx minus G1x minus, this is the usual supremum distance formula that we define on the space, or this is a vector space, or it is coming out from the what is called the sup norm that you have, and we know that therefore X is complete. That is a precondition. So you recall our fixed point theorem. If X is a complete metric space and T is a map from X to X, okay, which is a contraction, then there exists a unique fixed point. Okay, so this is the function space on which we are working. So we are now setting up the map, the transformation. G belonging to X, define TG X belonging to this is the definition. Okay. Now what we want to assert is that T is a map from X to X. The first thing that you observe is this. Tg at x0, this is equal to f of gx0, and what is that? Okay. And gx0 equal to y0, therefore this is equal to f of, now go to the definition of f of x0 y0, and this is equal to y. So this is the first observation that we make. Okay. So Tg x0 equal to y0. Now we compute this. Tg for any x on this interval, we will calculate this. then you see that by definition this is equal to f of x minus plus f of okay. Now this is just minus 1. Write one more. This is less than or equal to modulus of x gx minus f of x plus f of you add and then subtract the f of x y naught to it and then estimate it. Right. So that's it. Okay. What more? Is x here as at the moment? Then you can estimate this. You can estimate this, and this is less than or equal to we are applying mean value theorem. There is some beta that lies between this times gx y naught plus this part is delta 2 by 2, the way in which we have chosen delta 1. Okay. Now therefore this is again bounded by delta 2 by 2 so you can show that this is less than delta 2 by 2. Okay. And that implies P is a map from x to x. So T is a map from x to x. Okay, so that's the first part that we want to prove. Now we want to assert that. So that's the first assertion. Now we prove that contraction. T is a contraction. So let us estimate this. This is equal to which is equal to some eta, some point eta. We are applying this mean value theorem. Minus x, and this of course is less than or equal to 1 by 2. This is less than 1 by 2 into which implies T is a contraction. So we have defined a space X, and T is a map from X to X, and T is a contraction. So what is the consequence? So we can apply this, and you already shown that X is a complete metric space. So what do we conclude? Let us conclude. So we can apply the contraction mapping theorem directly, or just give the steps for this. So by the contraction mapping theorem, because X is now a complete metric space, and therefore you can apply T. There exists a unique such that X so okay, and what more you have? G equal to G. Now we can explain this out through sequences, or what you can say is define. We are in fact giving a proof of that. G naught X equal to Y naught. That is well defined. Henceforth, we designate this interval by J. Okay? And define Gn plus 1 etc. That means G1 is equal to Tg naught, etc. This is the Cutts approximation type argument. Tg naught etc. Now you look at this sequence Gn is uniformly and to a function G. Also Tg of x equal to f of x gx, and this is equal to limit n tending to infinity that's quite easy to follow. That is G belonging to x is the fixed point of and it is unique. Consequently, look at the function gx. Consequently, and f of look at the definition of capital F, that you will get this. So that completes one part of it. Now we have to show the remaining part of the theorem. Now we prove that G is differentiable on J and compute the derivative. Now fx and fy exists. on U and are continuous dx. So let x1 be such that mod delta 1, then f of x gx equal to 0, and hence we have f of x1 equal to 0. Thus, we have this 0 equal to which is equal to the usual technique. The usual technique, and this is equal to df by d. See, the first term varies in the second argument. Therefore, the dy by dy using Taylor approximation, or what you call mean value theorem. For some psi between x and x1 and theta between gx and to draw a picture to be clear. Therefore, into units. Okay, so we use this one, take the ratio, and this is what. Now it is follows immediately. And that's equal to minus by the continuity of the partial derivatives. And that completes the proof of the theorem. So we have shown the existence of a function g, and we have also computed the derivative of, we have shown that g derivative exists, and g derivative is computed in terms of the partial derivatives of f at x gx. Okay, so thank you very much. That concludes my lectures on metric spaces, and I will be returning to my earlier series, that is on Lebesgue integration theory, which I had left in the middle to take up these lectures on metric spaces for some some reasons of urgency. And now after this I will return to my return to consider the Lebesgue integration theory from where. Thank you very much.